$62 trillion per gram, explodes the moment it touches anything, could erase cities. But here's what's wild. This isn't even the rarest thing in the universe. Tonight, you're about to meet matter that converts planets' elements, that curse themselves to death, and discover the mystery of why you exist at all. Stay with me. This gets beautifully strange. If you're ready for the universe at its most extreme, leave a like drop, a comment with your guess what is the rarest thing, or simply listen. Let's begin. Deep beneath Switzerland, scientists just did the most dangerous thing in human history. They trapped something that could erase an entire city in an instant. Just 1 gram. Touch anything. Boom. Nothing left. This isn't science fiction. This is antimatter. And right now, in a laboratory 100 meters underground, researchers are holding it suspended in magnetic fields, praying it never touches the walls. Let me tell you what makes antimatter so terrifying. Picture holding a single gram in your hand, roughly the weight of a paperclip. That gram contains enough energy to equal 43,000 tons of TNT, the blast from 2 Hiroshima atomic bombs, from something lighter than a candy wrapper. The numbers sound impossible until you understand what happens when antimatter meets normal matter. Every particle you see around you has an evil twin lurking in physics equations. For every electron spinning in your body, there exists an opposite version with reverse charge. Scientists call this antimatter. When matter and antimatter touch, they don't just react chemically, they annihilate completely. Both vanish instantly, converting 100% of their mass directly into pure energy. No chemical reaction comes close to this efficiency. Burning gasoline releases energy stored in molecular bonds, maybe converting a tiny fraction of mass. Nuclear bombs split atoms and unleash about 1% of their fuel as energy. Antimatter converts everything. The entire mass. Nothing wasted. Einstein's famous equation E equals mc2 playing out in its most extreme form. Here's where it gets crazy. Antimatter is the most expensive substance in existence. Scientists estimate it costs approximately $62 trillion per gram. That's more than the combined GDP of 3 United States economies for 1 year. For 1 gram. But here's the problem. You can't keep it in your wallet. You can't store it in a safe. You can't put it in any container. The moment antimatter touches anything made of normal matter, both explode instantly. So how do scientists store it? They don't really. They levitate individual antiparticles in perfect vacuum chambers using powerful magnetic fields. Even then, storage times measure in minutes before particles escape and vanish in tiny flashes of energy. In 2011, researchers at Europe's largest particle physics laboratory achieved something that shouldn't exist. They created complete anti-atoms, not individual antiparticles floating alone, but actual anti-atoms with structure and stability. 100 atoms of anti-helium. Normal helium has 2 protons and 2 neutrons at its center, surrounded by 2 electrons. The anti-helium these scientists built contained 2 antiprotons and 2 antineutrons orbited by 2 positrons, a perfect mirror image of regular helium. The difficulty of this accomplishment defies imagination. First, you need a particle accelerator, 17 miles around running at nearly maximum power, consuming energy equivalent to powering hundreds of thousands of homes. Second, you must smash particles together at speeds approaching light velocity. Third, you must identify the few anti-helium atoms among billions of other collision products. Fourth, You must trap them before they touch anything and vanish. The team succeeded in creating exactly 100 complete anti-helium atoms. They existed for 3 millionths of a second before hitting detector walls and exploding into radiation. Think about that duration. 3 millionths of a second. Less time than it takes light to travel 1 kilometer. In that brief instant, these anti-atoms proved something extraordinary. Antimatter follows the same physical laws as normal matter. Now here's where your mind should start spinning. Right now, your body contains approximately 7 octillion atoms. That's a 7 followed by 27 zeros. Imagine if just one of those atoms were antimatter. Just one. You would explode with the force of a small bomb. The energy release would be catastrophic. But it doesn't happen. Every atom in your body is normal matter. Why compare antimatter weapons to hydrogen bombs? The most powerful nuclear weapons ever built achieve maybe 1% efficiency in converting mass to energy. An antimatter bomb would achieve 100% efficiency. 1 gram could devastate a city. 10 grams could match the largest nuclear weapons ever tested. Yet creating antimatter requires pumping in exactly the same energy you get from annihilation. You can't use it as practical fuel. The containment systems weigh thousands of times more than any antimatter they could hold. But nature produces antimatter constantly in small amounts. Lightning storms create positrons above thunderclouds. Every time you see lightning flash across the sky, you're watching a natural antimatter factory. The electrical discharge generates enough energy to create matter-antimatter pairs. Most annihilate immediately, but some positrons escape and drift in the atmosphere. You're standing beneath an antimatter generator and never knew it. Even more surprising, Earth itself traps antimatter naturally. The Van Allen radiation belts surrounding our planet contain small quantities of antiprotons. Cosmic rays slamming into atmospheric molecules at relativistic speeds create these antiparticles. Earth's magnetic field captures them, creating a natural antimatter mine floating in space around us. Satellites have detected these antiprotons circling at altitudes of several hundred miles. Some researchers suggest that somewhere in the vast universe, entire galaxies made of antimatter might exist. Anti-stars, burning anti-hydrogen, anti-planets, orbiting them, maybe even anti-life forms, wondering about matter galaxies. If such regions existed, they would look identical to normal matter galaxies from a distance. Light behaves the same, whether emitted by matter or antimatter atoms. The only way to detect them would be finding the boundary zones, where matter and antimatter regions meet. Particles from each side would mix and annihilate, constantly producing distinctive gamma-ray signatures. Satellites scan the cosmos for this telltale radiation pattern. So far, nothing confirmed. But here's the deepest mystery, the one that should keep you awake at night wondering. According to theory, the Big Bang created equal amounts of matter and antimatter. Perfect symmetry. For every particle, one antiparticle. They should have annihilated, completely leaving only energy. No atoms, no stars, no galaxies, no planets, no you. The universe should be nothing but radiation spreading through empty space. Yet here we are, somehow impossibly matter one. The current best guess involves a tiny imbalance in the first fraction of a second after the Big Bang. For every billion antimatter particles created, there existed 1 billion and one matter particles. That single extra particle in every billion became everything we see today. All the galaxies, stars, planets, trees, oceans, and people. Everything built from the leftover 0.001% after the Great Annihilation. Where did the antimatter go? Why did matter win by that precise margin? Some unknown process during the first second of existence tipped the scales. Physicists call this the Barrian asymmetry problem. It ranks among science's deepest mysteries. Solve it, and you explain why the universe exists at all instead of being just light. Dan Brown wrote about antimatter in Angels and Demons, imagining it stolen from laboratories and used as a weapon. The reality is both more and less dramatic than fiction. Yes, antimatter could theoretically be the ultimate explosive, but no, you can't steal enough to matter. The largest particle accelerator on Earth produces about 1/1000th of a gram per year. Creating just 1 gram would require running that machine continuously for 1 billion years. This is antimatter, the most expensive substance known, the most powerful explosive possible, the mirror image of everything you touch, and somehow, mysteriously, almost all of it vanished in the first instant of cosmic time, leaving behind just enough matter for you to exist, to wonder, to ask why. But this raises an even stranger question. If antimatter can vanish so completely, so mysteriously, what else might be hiding in physics? What other substances might exist at the edge of possibility, waiting to surprise us? Because antimatter isn't even the strangest thing we'll encounter tonight. Let that mystery settle for a moment. The vanishing of half the universe. Now, we descend deeper into the question, what really happened to antimatter? And could it still be out there, somewhere waiting? A crime occurred 13.8 billion years ago. Half the universe disappeared. No one knows who the culprit was, what mechanism drove the theft, and if this cosmic crime hadn't happened, you would never have been born. The evidence sits in every atom around you. The stars, planets, your body, everything you can touch consists of matter. Not antimatter, just matter. This seems natural until you realize it violates the symmetry of physics. When scientists run the equations backward to the Big Bang, they find something disturbing. Matter and antimatter should have been created in exactly equal quantities. Perfect balance. Then they should have met, annihilated, and left nothing but light spreading through empty space. But you're here. I'm here. Stars burn. Galaxies spiral. Something broke the symmetry. Think of it like this. Imagine you're watching a cosmic game with 1 billion antimatter particles on one side and 1 billion matter particles on the other. They rush together. Boom. Annihilation. Each particle finds its opposite, and both vanish in flashes of gamma rays. When the smoke clears, you expect nothing to remain. But instead, one lonely particle of matter survives. Just one. Out of 2 billion total participants, one extra matter particle had no antimatter partner to annihilate with. Now multiply that scenario across the entire early universe. Trillions upon trillions upon trillions of particles. In every batch of 1 billion pairs, one matter particle survived. Those survivors, that tiny 0.00 we will to percent excess, became everything. Every atom in every star, in every galaxy, came from leftover matter. You exist because of cosmic accounting error. Where did all the antimatter go? 3 hypotheses compete to explain the mystery, and each sounds more like science fiction than the last. First possibility, antimatter leaked into another dimension. Some theories involving extraspatial dimensions suggests that matter and antimatter might separate during the Big Bang, with antimatter draining away into realms we cannot access or detect. This would explain why we see only matter, but it requires accepting that hidden dimensions exist, that our familiar three dimensions of space plus time represent only a fraction of reality. Second possibility, a quantum process we don't understand occurred in the first second. During that initial instant, when the universe was incredibly hot and dense, maybe some unknown mechanism preferentially created matter over antimatter. Perhaps certain decay pathways favored matter by that crucial 1 in a billion margin. Particle physics experiments search for these slight asymmetries, and they've found hints. Certain exotic particles seem to decay into matter slightly more often than antimatter, but the effects measured so far are too small to explain the full imbalance. Something bigger must have happened in that first second. Third possibility, the wildest one, antimatter regions still exist somewhere in the universe, hidden beyond our detection range. Maybe the Big Bang didn't mix matter and antimatter uniformly. Maybe they separated into different cosmic neighborhoods. We live in a matter zone. Somewhere far beyond the observable universe, antimatter galaxies might cluster. This scenario seems unlikely because we'd expect to see boundary regions where matter and antimatter domains meet, producing constant gamma ray explosions as particles mix and annihilate. Telescopes scan the skies for such signatures. Nothing found yet. In 2011, scientists decided to test whether antimatter really behaves identically to matter. The experiment took years to prepare. They needed to create not just individual antiparticles, but complete anti-atoms with structure, then study them before they vanished. Picture the setup: a particle accelerator, 17 miles in circumference, buried underground, superconducting magnets cooled to near absolute zero, detectors capable of tracking individual particles among billions. The machine consumed enough electricity to power a small city, all to create 9 atoms. The team fired beams of particles, together at nearly light speed. Each collision generated a spray of debris, hundreds of particles flying in all directions. Computers analyzed every collision, searching for the telltale signatures of anti-helium formation. Most collisions produced nothing useful, but occasionally, rarely, the conditions aligned perfectly. An antiproton and 2 antineutrons bound together. 2 positrons captured into orbit around them. An anti-atom formed. Then came the hard part. These anti-atoms were moving at significant fractions of light speed. They would travel maybe a few meters before hitting something and exploding. The team needed to slow them down, trap them in magnetic fields, hold them stable, long enough to study their properties. They succeeded 9 times, 9 complete anti-helium atoms, each existing for about 30 billionths of a second before touching detector walls and vanishing in flashes of gamma rays. 30 billionths of a second. That's how long they had to confirm everything. The atoms showed identical spectral signatures to regular helium. Their structure matched perfectly. The strong nuclear force binding them together worked exactly the same. Antimatter follows the same rules as matter. This means antimatter could theoretically form anti-molecules, anti-chemistry, maybe even anti-life somewhere. Think about what this implies. Somewhere in the cosmos, There might exist an anti-Earth orbiting an anti-Sun, anti-trees growing in anti-soil under an anti-sky, anti-people walking around made of anti-protons, anti-neutrons, positrons, wondering about the universe just like you do right now. Now imagine you could meet your antimatter twin, your anti-self. They would look identical. Same face, same features. Light reflecting off them would appear completely normal. You wouldn't be able to tell them apart from a regular person just by looking. But the moment you shook hands, both of you would vanish in a catastrophic flash of energy, converting your combined mass entirely into gamma rays, a handshake with the power of multiple nuclear weapons. If antimatter regions exist in the universe, the boundary between matter and antimatter zones would be spectacular, a wall of constant gamma ray explosions stretching across cosmic distances. Individual atoms from each side would occasionally drift across the border, meet their opposites, and annihilate. The radiation signature would be unmistakable, visible from billions of light years away. Every telescope capable of detecting gamma rays searches for such boundaries. The fact that we find nothing suggests either antimatter regions don't exist, or they're beyond the observable universe's edge, or the separation was so complete that no mixing occurs. Here's something to think about when you look in a mirror tonight. You see your reflection, a reversed image of yourself. But an antimatter version of you wouldn't be reversed at all. They'd be identical in every way, except for their fundamental charge properties. And if you reached out to touch your reflection, and it were made of antimatter instead of glass and silver, you and the reflection would both cease to exist in an instant, transforming into pure light. The scientists who created those 9 anti-helium atoms spent billions of dollars and years of their careers for 30 billionths of a second of data. You might calculate the cost per unit time, roughly $100 million per billionth of a second. Netflix subscriptions suddenly seem reasonable in comparison, but they proved something profound. Antimatter can form stable structures. The laws of chemistry and atomic physics work the same way, regardless of whether you're using matter or antimatter. This opens theoretical doors. Could antimatter stars exist? Could antimatter chemistry be rich enough to support complex molecules? Could life arise in antimatter form? And this is just the beginning of tonight's story. Because if antimatter can mysteriously vanish from the universe, leaving only traces and questions, then what else might exist at the boundaries of physical law? What other substances might be waiting to surprise us? Things that don't just vanish mysteriously, but something worse. Things that could transform everything. They touch into something else. Matter that spreads like a virus, converting planets, stars, maybe entire galaxies into exotic forms we can barely imagine. Antimatter taught us that the universe plays with symmetry and breaks it for reasons we don't understand. Now, we'll meet substances that break reality in other ways, elements that curse themselves to death, matter that might be more stable than everything around you, waiting to transform the world at a touch. If you thought antimatter was strange, if you thought the mystery of the missing half-universe was unsettling, then prepare yourself. We're about to descend into even stranger territory, where elements destroy themselves, and matter itself might be living on borrowed time. Let those thoughts drift like antimatter particles through magnetic fields, never quite touching, always hovering at the edge of annihilation, ready for what comes next, because the universe has more impossible things to show you. Imagine something so hot it burns itself alive, no fire needed, no oxygen required, just existence. That's astatine element 85, the substance with the nickname Goodbye Element, because by the time you say hello, it's already vanished. Scan the entire planet. Check every rock formation, every ocean bed, every mountain peak. Search all 6 million trillion pounds of Earth. You'll find less than 1 ounce of this substance. 25 grams total. About 1 tablespoon. That's how rare astatine is across the entire world. Want to understand how impossibly scarce that is? Imagine trying to find astatine naturally. Take all of North America and South America combined. Dig down 10 meters everywhere. Sift through every cubic inch of soil and rock. You'd find approximately 0.003 grams, 3/10 billionths of a gram. That's roughly 1 trillion atoms spread across 2 continents. Finding a specific grain of sand on all Earth's beaches would be easier. Astatine sits on the periodic table, marked at element 85. The name comes from Greek, meaning unstable. That label undersells reality by a massive degree. Astatine atoms cannot exist for more than a few hours before self-destructing. The most stable version, astatine 210, survives 8 hours on average before splitting apart. Most forms last mere seconds. This rapid decay means any astatine present when Earth formed has long since vanished. The tiny amounts existing today form continuously through radioactive decay chains. When uranium and thorium atoms break down, they occasionally produce astatine as an intermediate step. That astatine then decays almost immediately into other elements. The process maintains roughly 25 grams spread across the entire planet at any moment. Why does astatine decay so rapidly? The nucleus contains 85 protons crammed into a space smaller than an atom. That many positive charges repel each other with intense force. The strong nuclear force barely holds them together. Any tiny quantum fluctuation breaks the balance, and the atom flies apart. Nobody has ever seen pure astatine in elemental form. Theory suggests it would appear as a dark, possibly metallic solid at room temperature. Scientists base this prediction on its position below iodine on the periodic table. Halogens get darker as they increase in mass. Fluorine appears nearly colorless. Chlorine shows yellow-green. Bromine glows red-brown. Iodine displays dark gray-violet. Astatine should be darker still. The prediction remains untested because accumulating enough astatine to see creates an insurmountable problem. Here's what would happen if you somehow gathered 1 milligram, roughly the size of a small grain of sand. That quantity contains about 3 quintillion atoms, 3 million trillion, all of them radioactive, all of them decaying. When astatine atoms decay, they eject particles at tremendous speeds. Those particles carry energy measured in millions of electron volts. Each decay releases heat. Now imagine 3 quintillion atoms all decaying within 24 hours. The calculation becomes terrifying. That sample would produce over 100 watts of power, continuously, about the same as a bright light bulb shining nonstop from a grain-sized piece of material. The temperature would spike to thousands of degrees within seconds. Solid astatine would melt. Liquid astatine would boil. gaseous astatine would glow white hot in the air, all within moments of formation. The entire sequence, solid to liquid to gas to dispersed vapor, would happen faster than you could blink. Any container would need active cooling systems to prevent the astatine from destroying itself and everything nearby. Think of it like this. You know how your phone gets warm when you use it for a long time. Now, imagine your phone heating up so intensely it melts. Then the molten metal boils. Then it vaporizes into gas, all in a few seconds. That's astatine in bulk, quantities that have never existed. The situation gets worse as you increase the amount. Double the astatine, and you double the power output. 10 times more material generates 10 times more heat. At some point, no cooling system could compensate. The sample would undergo runaway heating until complete vaporization. You could theoretically create an astatine bomb with no explosives, no trigger mechanism. Just gather enough astatine in one place. 1 microgram might be enough. It would naturally self-destruct from its own radioactive energy, heating itself beyond any material's tolerance. This self-destruction property makes astatine essentially impossible to study through conventional chemistry. Traditional methods require weighing samples, dissolving them, analyzing their crystal structures. Every technique assumes you can handle bulk material. With astatine, bulk material means working with billions of atoms instead of millions, quantities measured in picograms, trillionths of a gram. At these scales, individual atoms matter. Scientists have developed workarounds using tracer techniques. They mix astatine atoms with much larger quantities of similar elements, like iodine. The astatine follows the iodine through chemical reactions. Radiation detectors track where the astatine goes. This allows studying astatine's chemical behavior without ever having pure samples. Chemists call it the goodbye element for good reason. When researchers create astatine in particle accelerators, they have a brief window to study it. Hello, astatine, they might say. Goodbye. It responds and vanishes through radioactive decay. That's probably the shortest relationship in science. Most scientific instruments take longer to warm up than astatine takes to disappear. Despite its rarity and instability, astatine might become crucial for medicine. Astatine 211 emits alpha particles, high energy radiation, excellent at destroying cancer cells, while causing minimal damage to surrounding healthy tissue. Researchers attach astatine 211 to antibodies that target specific tumors. The antibodies deliver the astatine directly to cancer cells. The radiation acts like a microscopic bomb, destroying the tumor from within. But here's the challenge. You have 8 hours. 8 hours to produce the astatine in a nuclear reactor. 8 hours to purify it, attach it to the antibodies, transport it to the hospital, and inject it into the patient. Miss that window, and the astatine decays into something else. Hundreds of thousands of dollars worth of medical isotope becomes useless. It's a race against time, against physics itself, against the fundamental instability of matter. Current methods create only tiny amounts that must be used within hours of production. Hospitals must coordinate with nuclear facilities to receive shipments. Everything happens on a strict schedule, dictated by radioactive decay. The astatine arrives. Doctors prepare it. Patients receive treatment. All before the clock runs out. and the atoms transform into different elements. Picture an ice cube in your hand. Normal ice melts because heat from the environment transfers into it. But imagine an ice cube that generates its own heat from the inside. It doesn't need external warmth. It produces heat through its own internal processes, melting itself, then boiling itself, then evaporating itself into nothing. That's astatine, a suicidal element that cannot help but destroy itself. Every astatine atom contains a nuclear time bomb. The 85 protons packed into its nucleus maintain an unstable balance. When that balance breaks, the atom ejects particles at tremendous speeds, releasing energy, generating heat, driving its own destruction. The element literally cannot exist in quantities large enough to see, because visibility requires mass, and mass requires many atoms, and many atoms together generate too much heat to survive. If you think an element that destroys itself through its own radioactivity is bizarre, if you think matter that cannot exist in visible quantities sounds like the edge of possibility, then prepare yourself, because we're about to meet something worse, something that doesn't just destroy itself, but could destroy everything it touches. A chain reaction that cannot be stopped. A virus of matter that could consume planets, from self-destruction to something darker, transformation. What happens when matter doesn't die alone, but takes everything with it? There's a nightmare scenario that physicists whisper about, but rarely say out loud. A drop of strange matter falls to Earth. It touches ground, and in 1/10 of a second, the entire planet collapses into a sphere 100 meters across. 8 billion people, every city, ocean, mountain range, all of it compressed and converted into strange matter. This isn't science fiction. This is what the equations predict could happen, maybe under certain conditions, if strange matter exists and behaves the way some theories suggest. Everything around you is built from two types of quarks, up quarks and down quarks. These combine in threes to form protons and neutrons. 2 ups plus 1 down makes a proton. 2 downs plus 1 up makes a neutron. These combinations generate every atom in existence. Simple, elegant, universal. But nature actually provides 6 varieties of quarks. Up and down represent only the lightest pair. 4 heavier flavors exist with peculiar names, strange charm top and bottom. These exotic quarks appear in high-energy physics experiments, then decay almost instantly into their lighter cousins. Strange quarks earned their name from their peculiar behavior when first discovered. Particles containing strange quarks lived longer than expected and exhibited unusual properties. A strange quark weighs about 30 times more than an up or down quark. This extra mass makes strange quarks unstable under normal conditions. They decay through the weak nuclear force, transforming into lighter quarks within fractions of a second. Strange particles never survive long enough to incorporate into regular matter. Then theorists asked a simple question that opened a door to cosmic horror. What if strange quarks could become stable under extreme pressure? At normal densities, strange quarks immediately decay. But compress quarks together to extreme densities, and the rules change. Quarks are fermions, particles that obey the Pauli exclusion principle. This principle states that no 2 identical fermions can occupy the same quantum state simultaneously. Fill up all the low energy states with up and down quarks, and adding more quarks forces some to occupy high energy states. At some point, having a strange quark in a low energy state costs less energy than having a down quark in a high energy state. The strange quark becomes favorable. Here's what this means in plain terms. Everything around you, every proton, every neutron, every atom might be metastable, not truly stable, but temporarily stable. Like a ball sitting in a shallow bowl on a hilltop, it looks stable, but it's really just waiting for a push to roll downhill into a deeper valley. Strange matter might be that deeper valley, the true ground state, the lowest energy configuration possible. If this hypothesis is correct, then one day your atoms could realize they're in the wrong configuration. They could transform into something more stable, something denser, something called a strange quark matter. The conversion scenario plays out like this. A droplet of strange matter touches normal matter. Maybe it's a strangelet, a fragment of strange matter, the size of an atomic nucleus. Quarks from regular atoms touch it. They recognize the lower energy state. They convert to strange quarks. The newly converted material adds to the strangelet's mass. Energy releases in the transformation. That energy triggers conversion in nearby quarks. A chain reaction begins. The transformation propagates at close to light speed. Strange matter touches a nucleus. Quarks reconfigure within microseconds. Released energy triggers conversion in adjacent nuclei. A wave spreads outward in all directions. If started on Earth, such a wave would convert the entire planet to strange matter in about 1/10 of a second. Earth's diameter measures about 12,000 kilometers. Strange matter is incredibly dense, comparable to neutron star material. The planet's mass would remain constant, but its radius would shrink to about 100 meters. A sphere the size of a football field, containing everything Earth ever was. Every ocean, every mountain, every city, every person. All compressed into strange quark matter. Remember Kurt Vonnegut's novel, Cat's Cradle? The fictional substance called Ice-9, a form of ice that's more stable than regular ice. Touch it to liquid water, and the water instantly freezes into more Ice-9. The freezing spreads, converting all water on Earth into this new form of ice. The oceans freeze solid. Life ends. Vonnegut made it up as a warning about dangerous technology. Strange matter is the real version of Ice-9, but instead of ice, it's the densest possible form of matter. And instead of freezing water, it would convert everything. These theoretical droplets are called strangelets, fragments of strange matter, small enough to drift through space, but large enough to contain millions or billions of quarks. Strangelets might form whenever strange matter gets broken apart violently. When neutron stars collide, the impact might create cores of strange matter that fragment during the explosion. Each fragment becomes an independent strangelet shooting into space. They could be out there right now, drifting between stars, occasionally passing through solar systems, planets, maybe even your room as you listen to this. Right at this moment, a strangelet could be passing through you, invisible, undetectable, moving at cosmic velocities. But don't worry. If strangelets were dangerous in the way the nightmare scenario describes, we wouldn't be here to worry about it. The universe has already tested this scenario countless times. Cosmic rays strike Earth's atmosphere constantly. Some carry energies far exceeding anything human technology can produce. These cosmic rays create conditions similar to what happens in particle accelerators, but naturally billions of times over billions of years. If high-energy collisions could create dangerous strangelets that convert matter, it would have happened already. Earth would have converted long ago. In 2008, when scientists prepared to activate the Large Hadron Collider, some people worried the collider would smash protons together at unprecedented energies. Could it create strangelets? Could those strangelets fall into Earth's center and begin converting the planet from the inside out? The physicists explained patiently. Cosmic rays hit Earth with much higher energies than the Large Hadron Collider produces. If strangelets could form and were dangerous cosmic rays, would have created them billions of times already. The fact that we exist proves either strangelets don't form easily, or they aren't dangerous, or both. One person asked, "But what if this is the first time us?" A physicist reportedly answered, "Well, then we'll know very quickly. The Large Hadron Collider has been running for years now. No strangelets detected. No planet conversion initiated. We're still here. The experiment continues safely. But scientists do search for strangelets. They look in cosmic rays for particles with unusual mass-to-charge ratios. A strangelet would be far heavier than any normal nucleus with the same electric charge. They analyze meteorites for unusual isotopes that might indicate strange matter contamination. They even wonder if strangelets might have sunk to Earth's core billions of years ago, accumulated there waiting deep inside the planet in the highest pressure environments naturally available. Could strange matter be hiding? And there's another possibility. Maybe entire stars are made of strange matter. Strange stars. Not neutron stars with cores that might contain strange quarks, but objects composed entirely of strange quark matter from center to surface. Their surfaces wouldn't consist of atoms or nuclei, just bare quarks covered by thin electron atmospheres. When strange stars collide, they might fragment, sending strangelets flying through space at significant fractions of light speed. Those strangelets could be headed toward us right now. But remember, cosmic rays test these scenarios constantly. Nature runs the experiment trillions of times. If matter conversion through strange contamination were possible, it would have happened. The universe is nearly 14 billion years old. Plenty of time for statistical flukes. Yet here you are. Here we all are. That's evidence, not proof, but strong evidence that the nightmare scenario doesn't happen. And now you understand why we call this the weapons of the cosmos. We've met antimatter, the perfect explosive that converts mass to energy with 100% efficiency. We've encountered astatine, an element that destroys itself through its own radioactivity, unable to exist in visible quantities. And now, strange matter, a theoretical substance that could convert entire planets in fractions of a second, spreading like a virus through normal matter. But there's one more mystery before we rest. One final puzzle. Not something that destroys or converts, but something that simply refuses to exist. An element cursed by physics itself, forbidden from remaining in our reality for more than hours at a time. A gap in nature's collection, a hole in the periodic table, and the question of why some things are permitted to exist while others are not. One more turn in tonight's journey, from matter that destroys to matter that simply refuses to be, in the periodic table between elements 60 and 62, there's a gap. Not an accident, not a mistake, a curse. Element 61 cannot exist for long. It's as if nature says, you may come into being, but you cannot stay. This square is forbidden. But why? And are there other forbidden zones hiding in reality waiting to be discovered? Picture the periodic table as a map of existence. Each element represents a square of ground you can stand on. Hydrogen solid, carbon solid, iron, gold, uranium, all stable territory. Elements 1 through 94 stretch across this landscape, but element 61, that square collapses beneath you. Step on it, and you fall. You can exist there briefly, but physics refuses to let you remain. Are there other cursed squares we haven't found? Other holes in space, in time, in dimensions beyond our perception? Between 1920 and 1940, the hunt for element 61 became an obsession. Multiple research teams across the world announced they'd found it. Italian chemists claimed discovery. American groups published their results. Each time, excitement spread through the scientific community. Finally, the gap would be filled. The periodic table would be complete. Each time they were wrong. Not lying, not fabricating data. They genuinely believed they'd isolated element 61. They ran careful experiments, analyzed samples, measured spectral lines. They published in peer-reviewed journals. Other scientists examined their work, and gradually, inevitably, the truth emerged. The supposed element 61 signatures came from other elements. Experimental contamination, misidentified spectral lines, wishful thinking transforming noise into signal. The mystery deepened with each failed claim. Why couldn't anyone find this element? Its neighbors existed abundantly. Neodymium element 60 appears in minerals worldwide. Samarium element 62 is common enough for industrial applications. Between them should sit element 61 with similar properties, similar abundance. Yet every search came up empty. Nature seemed to have skipped a number. In 1945, scientists at Oak Ridge National Laboratory finally solved the puzzle, though the solution raised deeper questions. They created element 61 artificially by bombarding uranium with neutrons in a nuclear reactor. The process produced it as a fission byproduct. They isolated microscopic amounts and confirmed its properties. The element existed. They named it promethium, after the Greek titan Prometheus. But here's why no one had found it naturally. Every single isotope of promethium is radioactive, with a relatively short half-life. The most stable version, promethium-145, survives approximately 18 years on average before decaying. 18 years. That sounds reasonable until you compare it to Earth's age, 4.5 billion years. The most stable promethium lasts roughly 1/250 millionth as long as our planet has existed. Do the math. Any promethium present when Earth formed 4.5 billion years ago has long since decayed away. 18 years versus billions of years. It's not even close. Promethium cannot accumulate. It cannot persist. It appears briefly through natural processes, then vanishes, transforming into samarium. Today, promethium exists on Earth only through continuous production. Natural uranium undergoes spontaneous fission occasionally. This rare process creates tiny amounts of promethium among the fission products. Scientists estimate perhaps 500 grams exist naturally across the entire planet at any moment. That's about 1 pound, spread across the whole Earth. and constantly decreasing. As atoms decay faster than new ones form, the element's name carries its own curse, a warning written in mythology. Prometheus, the titan who defied the gods. He stole fire from Olympus and gave it to humanity. For this crime, Zeus punished him eternally. Chains bound Prometheus to a mountain. Each day an eagle came and ate his liver. Each night the liver regenerated. Each dawn the eagle returned. Endless punishment for bringing forbidden knowledge to mortals. Prometheum is that stolen fire, something that shouldn't exist in our world, or at least shouldn't exist for long. Reality itself punishes its existence. The element appears, persists briefly, then decay forces transformation. Like Prometheus's liver growing back only to be devoured again, the cycle continues. Uranium fissions creates promethium. Promethium decays to samarium. Somewhere else more uranium fissions, more promethium appears. Brief existence, then transformation, forever. Despite its rarity and instability, promethium possesses strange, almost supernatural properties. It glows in darkness, not like phosphorescent materials that absorb light and slowly release it. Promethium generates its own light continuously through radioactive decay. The decay process itself excites electrons in surrounding material, causing emission of blue-green light. No external energy source needed, no charging required, just perpetual, ghostly illumination powered by nuclear transformation. A sample of promethium salt shines in complete darkness. This property seemed perfect for practical applications. Watchmakers painted promethium onto clock faces. The watches glowed at night without batteries or external light. Instrument panels in aircraft used promethium for visibility in darkness. Then, people realized the workers painting these dials faced dangerous radiation exposure. The users wearing these watches accumulated dose over time. Safety concerns ended these applications. The ghostly glow was banned. Promethium also powered some satellite batteries. Radioactive decay generates heat. Thermoelectric generators convert that heat directly to electricity. Spacecraft could carry promethium oxide as a power source, generating electricity reliably for years. The technology works. The physics is sound. But promethium's extreme rarity and enormous production cost made it impractical. Modern satellites use other radioactive isotopes or solar panels instead. Here's where promethium becomes a witness to cosmic death. Astronomers occasionally detect promethium in dying stars. When massive stars exhaust their hydrogen fuel and begin fusing heavier elements in desperation, they create promethium through nuclear reactions. Analyzing starlight sometimes reveals promethium's characteristic spectral lines, proving active nuclear fusion continues in the stellar atmosphere. The element exists briefly before decaying into samarium, but during that window, it leaves a signature, a death certificate written in light. Stars create promethium only when burning their final fuels, desperately trying to sustain fusion against gravitational collapse. Finding promethium in a star's spectrum tells astronomers that star is dying. It's creating elements that cannot persist, elements that decay before the light reaches our telescopes. Promethium becomes the signature of stellar death, encoded in wavelengths, traveling across space for millions or billions of years. Imagine you're an element. You want to exist. You want to participate in chemistry form, molecules, build structures, persist through time, but the universe says no. You may briefly appear. Reality tells you, but you cannot stay. 18 years maximum. Then you must become something else. That's promethium, the struggle to exist rejected by physics itself. Have you ever felt something similar? Wanted something to last, tried, holding onto it, but watched it slip away despite your efforts? Promethium embodies that feeling, the element that technically exists but cannot persist, temporary by nature, forbidden from permanence. Promethium is like that unreliable friend who promises to attend your party, shows up for 5 minutes, then leaves. You say, "Hey, stay longer." They respond, "Can't help it, I've got a half-life." And they transform into samarium right before your eyes. If elements had personalities, promethium would be the flakiest one in the periodic table. Or think of it like reality's version of Snapchat, messages that appear then self-destruct automatically. Except promethium's timer runs 18 years instead of 10 seconds. That seems substantial until you remember the universe is nearly 14 billion years old. 18 years compared to 14 billion. Still fundamentally temporary, still essentially instant on cosmic timescales. Why is element 61 forbidden from long existence? Why does physics place this specific curse on this particular arrangement of protons and neutrons? Are there other forbidden numbers we haven't discovered? Other constants or quantities that reality refuses to permit? And in some parallel universe with different physical laws, does stable promethium exist, forming mountains and oceans and perhaps even life? We've traveled quite a distance tonight. We started with antimatter, the perfect explosive, capable of erasing cities with grams of material. We met astatine, the self-immolating element that destroys itself through its own radioactive heat before visible quantities can accumulate. We encountered strange matter, the theoretical substance that might convert entire planets into dense quark matter in fractions of a second. And now promethium, the element cursed to brief existence, forbidden by fundamental physics from persisting naturally. All these share something profound. They exist at the boundary of what reality permits, as though the universe is testing its own limits, exploring how far physical laws can stretch before snapping. Antimatter that annihilates on contact. Elements that self-destruct faster than they can accumulate. Matter that could spread like a cosmic virus. Elements that cannot exist naturally at all. Each one pushes against the edges of possibility, showing us where the boundaries lie. But if you think these materials represent extremes, if you believe we've explored the limits of cosmic strangeness, prepare yourself for what comes next. We're leaving laboratories and periodic tables behind. We're heading into space itself, to objects where these rare materials might exist in bulk. Neutron stars, where 1 teaspoon weighs 1 billion tons. Strange stars potentially composed entirely of that virus-like matter we discussed. And magnetar stars with magnetic fields powerful enough to rip atoms apart from 1,000 kilometers away. Places where physics doesn't just approach its limits, but crashes straight through them into territory we're still struggling to comprehend. Let these images settle gently now. Antimatter, exploding on contact. Astatine, burning itself to nothing. Strange matter, spreading through planets. Promethium appearing and vanishing like ghosts. All real, all waiting at the edges of what the cosmos allows. Tonight, you're safe here. But somewhere in the vast universe, these impossible things actually happen. Rest now, with that wonder, with that mix of danger and beauty that defines reality's far frontiers. The next part of our journey waits, but for now, let these thoughts drift softly away, like promethium atoms decaying into dreams. Sleep well, and wonder about the mysteries still waiting to unfold. We've explored a matter at its strangest on Earth, substances that explode self-destruct or threaten to convert everything they touch. Now we leave our planet behind and venture into space where entire stars are made from materials so extreme they make antimatter seem tame. Take a teaspoon, fill it with neutron star material, place it on a scale. The needle would read 4 billion tons. This weight would crush through the scale, through the floor, through Earth's crust, and sink toward the planet's core. That's the density we're dealing with. Matter compressed beyond normal limits. Neutron stars represent what happens when massive stars die violently. When a star 8 times heavier than our Sun exhausts its fuel, the core can no longer support itself against gravity. The outer layers explode outward in a supernova, one of the brightest events in the universe. The core collapses inward. Atoms get crushed into oblivion. Electrons get forced into protons, creating neutrons. Those neutrons pack together so tightly that a city-sized sphere contains more mass than our entire sun. Picture compressing all of humanity, 8 billion people, into a space the size of a sugar cube. That approaches neutron star density. Every cubic inch contains the mass of Mount Everest. The pressure inside these objects defies description. At the surface, gravity pulls with 100 billion times Earth's force. If you could somehow stand on a neutron star and drop a pebble from 1 inch above the ground, that pebble would accelerate to thousands of miles per hour before impact. Mountains on neutron stars cannot rise more than a few millimeters before gravity flattens them. The surface itself displays bizarre properties. Scientists believe it forms a crystalline lattice of iron nuclei frozen into the hardest material in the universe. This crust measures perhaps 1 mile thick and possesses strength trillions of times greater than steel, yet it floats on something stranger beneath. Below the crust exists an ocean of superfluid neutrons. These neutrons flow without friction, without viscosity, without any resistance. They form a quantum liquid that behaves unlike any normal fluid. Waves in this ocean would propagate forever, never damping or dissipating. Diving deeper reveals more extreme conditions. Neutrons pack so tightly they begin touching. Remember that neutrons themselves have internal structure. Each contains 3 quarks held together by the strong nuclear force. Under neutron star pressures, those quarks might break free from their confinement. This possibility leads to fascinating speculation. If pressures grow high enough to dissolve neutrons completely, the quarks might rearrange into different patterns. Theory suggests this transition happens at about twice normal nuclear density. Many neutron stars likely reach these conditions at their cores. What exists there remains uncertain. Ordinary matter cannot exist. Neutron matter probably cannot exist. Something else must fill that space. Perhaps free-floating quarks forming a quark liquid. Perhaps even stranger arrangements we haven't imagined yet. Observing neutron stars provides clues about their interiors. When neutron stars spin They emit beams of radiation, like cosmic lighthouses. These pulsars flash with incredible precision. Some keep time more accurately than atomic clocks. The spin rates, gravitational effects, and cooling patterns all reveal information about internal structure. Recent observations detected neutron stars more massive than scientists predicted. The heaviest confirmed examples contain about twice the mass of our Sun, compressed into a sphere 12 miles across. Theory suggested such massive neutron stars should collapse into black holes. Their existence pushes models to extreme limits. These massive neutron stars might contain exotic forms of matter, stabilizing them against collapse. When two neutron stars collide, they create the most violent events in the cosmos, short of supernovas. The collision melts both stars, sending shock waves through the neutron fluid. Material gets ejected at substantial fractions of light speed. The merger might form a more massive neutron star or collapse directly into a black hole. Gravitational wave detectors have captured signals from multiple neutron star mergers. The waves carry information encoded in their pattern. By analyzing the signals, scientists estimate how stiff or soft neutron star matter behaves. Stiff matter resists compression and allows larger neutron stars. Soft matter compresses easily and limits maximum masses. Current data suggests neutron star matter behaves stiffer than many models predicted. This implies the strong nuclear force remains powerful even at extreme densities. The quarks inside neutrons might resist dissolving into free quarks longer than expected. These stars represent matter at the edge of stability. Any denser, and they would collapse into black holes. Any less dense, and they would just be ordinary dead stellar cores. They occupy a narrow band between normal matter and the ultimate compression of a singularity. They're nature's experiment in how much you can squeeze matter before it gives up and becomes something else entirely. And here's something that should make you pause. These objects exist scattered throughout our galaxy. Right now, thousands of neutron stars orbit through space, each one a laboratory of extreme physics, each one demonstrating that reality permits densities we can barely imagine, each one stable, persistent, waiting for us to understand them better. But neutron stars might not represent the final word on dense stellar remnants. There's a possibility, still theoretical, but growing more plausible, that some stars compress beyond even neutron star density into something fundamentally different, from the merely extreme to the truly exotic. Imagine stars without atoms at all. What if some neutron stars aren't really neutron stars at all? What if there's something stranger, denser, made from matter in its most fundamental form? The hypothesis sounds simple but radical. Instead of neutrons packed together, imagine free quarks floating in a liquid. No neutrons, no protons, no atomic nuclei whatsoever. Just quarks interacting directly through the strong nuclear force. An entire star 12 miles across, composed entirely of strange quark matter from center to surface. These hypothetical objects are called strange stars. They would look similar to neutron stars from a distance. Both are roughly the same size. Both possess powerful magnetic fields. Both spin rapidly and emit radiation. But their internal composition would be fundamentally different. A neutron star has layers: the iron crust on top, the superfluid ocean beneath, the core where neutrons might dissolve into quarks. But a strange star, no layers, no crust, just strange quark matter extending from the center to the surface, covered only by a thin electron atmosphere, perhaps 100 feet thick. Imagine a star without a shell, like a giant water droplet, but instead of H2O molecules, held together by surface tension, its quarks held together by the strong nuclear force. The surface would be bare quarks, touching vacuum. No atoms, no nuclei, nothing between the quark liquid and empty space, except a thin layer of electrons neutralizing the electric charge. This sharp boundary affects how the star appears in different wavelengths. Neutron star atmospheres contain atoms that absorb and emit radiation at characteristic wavelengths. Strange star atmospheres lack atoms entirely. Their X-ray spectra should show different patterns, possibly including features from free quarks interacting with photons. Several compact objects have been proposed as strange star candidates. One famous case involves RxJ 1856, an isolated neutron star relatively close to Earth. Initial measurements suggested it appeared too small for its temperature inconsistent with standard neutron star models. Strange star models fit the data better. Later observations complicated the picture. Different instruments obtained varying results. Currently, RxJ 1856 remains a possible strange star candidate, but far from confirmed. How would you distinguish a strange star from a neutron star? The cooling rates differ. Strange stars might cool faster because quarks can emit neutrinos directly through weak interactions. This creates an efficient cooling channel unavailable to neutron matter. Observing the temperature of compact objects at various ages could reveal which cooling mechanism dominates. The X-ray emission provides another test. Comparing spectra from candidate strange stars to neutron star predictions might identify differences. The surface properties of bare quark matter versus atomic nuclei should produce observable signatures. Sensitive X-ray telescopes could potentially detect these distinctions. If strange stars exist, their collisions would be spectacular and terrifying. When two strange stars merge, they produce hot, strange quark matter under extreme conditions. The merger might eject droplets of strange matter in all directions. Those droplets, if stable, would become strangelets propagating through the galaxy. Remember our discussion of strangelets potentially converting normal matter. Strange star collisions might be their source. Think about that implication. If strange stars are common and collisions frequent, billions of strangelets might drift through interstellar space. Some could pass through our solar system. A few might even strike Earth, though their small size would make detection nearly impossible. Strange stars challenge our understanding of matter's ground state. If they exist, they prove that quarks can form stable bulk matter outside normal particle confinement. They validate entire branches of theoretical physics. They open questions about whether all neutron stars might eventually convert to strange stars over time. The search continues with improving technology. New X-ray telescopes offer better spectral resolution. Gravitational wave detectors become more precise with each upgrade. Each advancement brings us closer to definitively identifying or ruling out these exotic objects. And if you think neutron stars are extreme, if you believe strange stars push the boundaries of possibility, wait until you meet their magnetic cousins. objects so powerfully magnetic they warp space itself. Density gives way to another extreme: magnetic fields beyond imagination. Earth has a magnetic field. Compasses detect it. It shields us from solar radiation. Its strength measures about half a Gauss at the surface. This field seems adequate for its protective role. Now multiply that strength by 10 quadrillion. You've reached magnetar territory. Magnetars are neutron stars with magnetic fields so powerful they warp quantum vacuum itself. These fields reach 1 quadrillion Gauss at the surface. At a distance of 1,000 kilometers, a magnetar's magnetic field would erase every credit card on Earth. It would disrupt cellular processes. It would potentially affect molecular bonds, pulling on the electron clouds that hold atoms together in molecules. Earth's magnetic field helps you use a compass to navigate. A magnetar's magnetic field could pull iron atoms out of your blood from 1,000 kilometers away. You definitely wouldn't want to try that experiment. Only about 30 confirmed magnetars exist in our galaxy. They form when neutron stars are born with extremely rapid rotation rates. The spin combined with turbulent convection in the hot proto-neutron star generates magnetic fields through a cosmic dynamo process. The fields trap and amplify during collapse, concentrating enormous magnetic flux into a small volume. The resulting magnetic field stores energy equivalent to the star's rotational energy. This creates an unstable situation. The field wants to reconfigure to lower energy states. When it does, the stored energy releases explosively. Magnetar flares are the most violent electromagnetic events in the universe, besides gamma ray bursts. In less than 1 second, a magnetar can release more energy than our sun emits in 100,000 years. This energy erupts as X-rays and gamma rays that flood interstellar space. One particularly powerful flare in December 2004 originated from a magnetar about 50,000 light years away. Despite the enormous distance, the radiation flash temporarily overloaded multiple satellites and affected Earth's ionosphere. If the magnetar had been only 10 light years away, the flare might have caused mass extinction on our planet. Think about that. A stellar object 50,000 light years distant, creating measurable effects on Earth through pure electromagnetic radiation. The magnetic fields create bizarre effects near magnetar surfaces. Light does not travel straight through such strong fields. Photons split into 2 polarization modes that propagate at different speeds. This vacuum birefringence makes space itself optically active. Light beams bend and twist in ways impossible under normal conditions. It's like turning on an air conditioner, but instead of cooling the room, it creates a magnetic storm powerful enough to shred atoms into their component particles. Atoms cannot maintain normal structure in these fields. Electron orbitals become elongated into cigar shapes, aligned with the magnetic field. Chemical bonds break or form differently. Matter becomes magnetically controlled at the atomic level. Even the vacuum exhibits strange behavior, with virtual particle pairs aligning before annihilating. The crust experiences unimaginable stress. Magnetic pressure tries to expand the star outward. Gravity tries to compress it inward. The two forces create strains that would shatter any normal material. The crust develops massive internal tensions that build over time. Eventually, something must give. The crust cracks suddenly in a starquake. Magnetars might also be responsible for fast radio bursts, mysterious millisecond duration, radio pulses detected from distant galaxies. When magnetar crusts crack, the sudden energy release could accelerate particles to extreme velocities. These particles, radiating coherent radio waves as they stream through the star's magnetic field, could produce the observed bursts. Recent discoveries found magnetars with lower magnetic fields than expected. These objects blur the line between magnetars and regular pulsars. Their existence suggests the magnetar phenomenon might be more common than previously thought, with a spectrum of field strengths rather than a sharp division. The interior of a magnetar might contain exotic matter formed under extreme magnetic influence. Strong fields could modify the phase diagram of nuclear matter. New types of matter with unusual properties could become stable. Quarks inside magnetars experience magnetic effects directly. In sufficiently strong fields, they might align and organize differently than in ordinary neutron stars. These stars prove that nature creates conditions more extreme than anything achievable in laboratories. Their magnetic fields exceed human technology by factors of trillions. Their energy releases dwarf our most powerful devices. They operate in regimes where quantum mechanics becomes nonlinear and vacuum itself gains properties we're only beginning to understand. From magnetic monsters to something even older, objects born not from dying stars, but from the universe's first moments. The first stars didn't light up until about 100 million years after the Big Bang. Before stars existed, before galaxies formed, before atoms assembled, tiny black holes might have appeared. These primordial black holes didn't form from stellar collapse. No star existed to collapse. Instead, they condensed directly from density fluctuations in the extremely hot, dense early universe. Random quantum variations during cosmic inflation created regions slightly denser than their surroundings. When inflation ended, those overdense regions collapsed under their own gravity. The timing matters critically. During the first second after the Big Bang, the universe's density was enormous. Any fluctuation above a certain threshold would collapse immediately into a black hole. These primordial black holes could have any mass from microscopic to millions of times our sun's mass, depending on when and how they formed. The lightest ones would be truly tiny. A black hole with the mass of Mount Everest would measure only 1 nanometer across. One with the mass of a large asteroid would be about the size of a proton. These microscopic black holes would be far smaller than atoms, yet contain more mass than mountains. These objects are older than everything else, older than stars, older than galaxies, older than planets. They witnessed the entire history of cosmic evolution. They predate everything we can see in the night sky. They're fossils from creation itself, floating through space unchanged, except for slow evaporation. Primordial black holes offer a possible explanation for dark matter, the invisible substance comprising 85% of the universe's matter. If many primordial black holes formed with masses between that of the moon and our sun, they would be extremely difficult to detect individually, yet would gravitationally influence galaxies and galaxy clusters exactly as dark matter does. Testing this hypothesis involves several approaches. gravitational microlensing can detect compact objects passing between Earth and distant stars. When a primordial black hole crosses our line of sight to a star, its gravity bends the starlight and causes brief brightening. Surveys monitoring millions of stars have found some candidate events. The frequency of microlensing events limits how much dark matter can be primordial black holes. If they comprised all dark matter, we would see more microlensing than observations reveal. Current data suggests primordial black holes might account for a few percent of dark matter at most. Something else must dominate. Another test involves gravitational waves from black hole mergers. When LIGO detected colliding black holes with unexpected masses, some researchers proposed they might be primordial rather than stellar in origin. Stellar evolution struggles to produce black holes in certain mass ranges. Primordial formation has no such constraints. The debate continues. Some gravitational wave events favor primordial interpretations. Others clearly match stellar black holes. A mix seems likely with some mergers involving primordial black holes and others involving stellar remnants. Separating the two populations requires detailed statistical analysis. Primordial black holes might explain other cosmic mysteries. Supermassive black holes at galaxy centers grew extremely quickly in the early universe. Standard formation scenarios struggle to explain such rapid growth. If primordial black holes served as seeds, the supermassive black holes could have started with substantial mass and accreted from there. Very small primordial black holes would have been extremely hot. Temperature increases inversely with mass for black holes. Microscopic black holes would radiate, intensely losing mass through Hawking radiation. The lightest ones would have evaporated by now. Any primordial black hole lighter than about 100 trillion kilograms would have completely radiated away its mass over the universe's 14 billion year lifetime. Only heavier ones survive to the present day. This evaporation sets a lower mass cutoff for detectable primordial black holes. We cannot find ones that formed too light because they no longer exist. The remaining population consists only of black holes massive enough to survive until today. Between the upper limit from microlensing and the lower limit from evaporation lies a window of masses where primordial black holes could hide. This window might contain enough to explain some dark matter observations while remaining below detection thresholds. Recent theoretical work explored whether primordial black holes could form in the first fraction of a second after the Big Bang. During cosmic inflation, quantum fluctuations might have created overdense regions that collapsed as soon as inflation ended. These ultra-early black holes would have unusual properties compared to later ones. The mass function depends on the detailed physics of the early universe. Different inflation models predict different amounts at various masses. Observational constraints from multiple sources combine to rule out large regions of parameter space. Only certain formation scenarios remain viable. Some models predict primordial black holes should cluster together in dense groups. These clusters would behave like dark matter halos. Galaxies forming inside such halos would have primordial black holes scattered throughout. Occasional interactions between primordial black holes and stars might produce distinctive signals. The search continues with improving sensitivity. New gravitational wave detectors can find lighter black hole mergers. Better microlensing surveys monitor more stars. Each method constrains different mass, ranges, and formation scenarios. If primordial black holes exist, eventually someone will catch definitive proof. And now we turn from the extremely large to the extremely small, from black holes that could be millions of times heavier than our sun to ones that would fit inside an atom. Size becomes irrelevant when dealing with black holes. What matters is mass compressed to impossible density. A black hole with the mass of a small asteroid would measure smaller than a proton. Its event horizon would span about 1 femtometer, roughly the size of an atomic nucleus. This micro black hole would contain more mass than Earth's largest mountains, compressed into a space tinier than a single atom. Such objects seem purely theoretical. No known natural process creates black holes this small. Stellar collapse produces black holes at least 3 times our sun's mass. Primordial formation during the Big Bang might have created smaller ones, but most would have evaporated by now through Hawking radiation. Yet under specific conditions, micro black holes could form briefly. When extremely high energy particles collide, they might compress energy into small enough volumes to create temporary event horizons. Cosmic rays striking Earth's atmosphere at near light speed carry enormous energies, occasionally reaching levels that could, in principle, form micro black holes. It's hard to imagine something smaller than an atomic nucleus, but heavier than Mount Everest. Physics permits it. The equations allow it. Whether nature actually creates such objects remains unknown. Particle accelerators were specifically designed to test this possibility. When the Large Hadron Collider began operations, some researchers predicted it might create microscopic black holes. These would not be dangerous. A micro black hole would evaporate essentially instantly, far too quickly to consume any appreciable matter. The predictions depended on theories involving extra dimensions of space. If gravity becomes stronger at tiny distances due to hidden dimensions, then black holes could form at lower energies than expected. The collider's proton beams might have sufficient energy to create micro black holes regularly. Experiments searched for characteristic signatures. Micro black holes should decay through Hawking radiation into sprays of various particles. The decay products would appear as high-energy jets with specific statistical properties. Detectors analyzed millions of collisions, looking for this pattern. No convincing micro black hole signals appeared. Either the formation energy exceeds what colliders can achieve, or hidden dimensions don't exist, or black holes don't form in the predicted manner. The null result constrained theories about extra dimensions and quantum gravity. In 2008, when scientists prepared to activate the Large Hadron Collider, some people worried. Could it create black holes? Could those black holes fall into Earth's center and begin consuming the planet from the inside? The physicists explained patiently, repeatedly. Cosmic rays hit Earth with much higher energies than the LHC produces. Nature has been running this experiment for billions of years. If high-energy collisions could create dangerous black holes, cosmic rays would have done it trillions of times already. The fact that we exist That we're still here drinking coffee and worrying about things proves either micro black holes don't form easily, or they're not dangerous, or both. One person reportedly asked, "But what if this is the first time it happens?" A physicist answered something like, "Well then, we'll know very quickly. The LHC has been running for years now. No black holes detected, no planet consumption initiated. We're still here. The coffee still tastes good. The experiment continues, safely teaching us about particle physics without creating cosmic disasters. Micro black holes would possess peculiar properties if they could be created and studied. Their small size means their Hawking temperature would be enormous. Temperature scales inversely with mass. A black hole with mountain mass would have a temperature of billions of degrees. At such temperatures, the black hole radiates all types of particles. The evaporation time depends on initial mass. A black hole with the mass of Mount Everest would completely evaporate in about 1 second. Smaller ones vanish faster. Larger ones last longer. The relationship follows a cubic law. Double the mass, and evaporation time increases 8-fold. Near the end of evaporation, the process accelerates dramatically. The black hole radiates faster as it shrinks. The temperature increases, driving even more radiation. Power output surges exponentially. In the final microseconds, the black hole releases as much energy as a nuclear bomb. This terminal explosion should produce a characteristic burst of high-energy gamma rays and particles. Satellites and ground telescopes search for such bursts, scanning the sky for sudden flashes, matching the predicted spectrum. Finding even one would provide the first observational evidence for Hawking radiation. Decades of searching have produced no confirmed detections. The absence limits how many primordial black holes can be evaporating today. If they were common, we would see their death bursts regularly. These non-detections tell us something important about nature. At the energy scales, we can probe gravity behaves according to Einstein's theory, without significant modifications. Whatever exotic physics governs quantum gravity must wait for higher energies to manifest. Tonight, we've journeyed from neutron stars, where teaspoons weigh billions of tons, to strange stars that might be made of bare quarks, to magnetars with magnetic fields that warp space itself, to primordial black holes older than stars, and finally, to micro black holes smaller than atoms. Each one pushes physics to its limits, and sometimes beyond. Let these images settle gently now. Stars compressed to city size, magnetic fields strong enough to tear atoms apart from thousands of kilometers away, black holes from the universe's first instant, singularities smaller than nuclei, all real possibilities, all waiting at the edges of what nature permits. Rest now with these thoughts, drifting softly like cosmic dust. Tomorrow brings new mysteries, deeper questions about the fabric of reality itself. But tonight, let yourself float among these extreme objects, marveling at how strange and beautiful the universe becomes when physics reaches its limits. Sleep well, knowing that somewhere out there, these impossible things actually exist. Black holes trap everything. Light cannot escape. Matter disappears forever across the event horizon. This seemed absolute until 1974, when Stephen Hawking revealed something impossible. Black holes glow. The discovery emerged from combining quantum mechanics with general relativity. Near a black hole's event horizon, quantum fluctuations create temporary particle pairs from empty space. Normally, these pairs annihilate immediately, borrowing energy from vacuum uncertainty for brief instants before returning it. But if one particle forms just inside the horizon, while its partner appears just outside, they separate permanently. The particle outside escapes as real radiation. The particle inside falls into the black hole, carrying negative energy that reduces the hole's mass. From a distance, the black hole appears to emit particles and shrink slowly. Hawking called this thermal radiation. The black hole has a temperature, radiates like a hot object, and gradually evaporates. The effect seems impossibly weak for typical black holes. A black hole with our sun's mass would have a temperature of only 1/1,000,000th of a degree above absolute zero. The cosmic microwave background radiation is far warmer. Such black holes absorb more energy than they radiate. They grow rather than shrink. But smaller black holes radiate more intensely. Temperature increases as mass decreases. It's like having a strange refrigerator. The bigger it is, the colder it runs. The smaller it is, the hotter it gets. A black hole, weighing as much as Mount Everest, would glow at billions of degrees. One with Earth's mass would be barely warmer than the cosmic background. The crossover happens at specific masses where absorption and emission balance. For the first 40 years after Hawking's prediction, nobody observed this radiation from any black hole. The effect remained purely theoretical. Every black hole, detected through telescopes or gravitational waves, was far too massive to show measurable Hawking radiation. Their temperatures stayed essentially absolute zero. This presents a fundamental challenge. How do you detect something that produces less radiation than it absorbs stellar mass black holes? Sit in space bathed in cosmic microwave background at about 3 degrees Kelvin. Their Hawking temperature measures far below that. They're invisible, not because they're black, but because they're colder than their surroundings. Micro black holes offer the only hope for detection. A black hole with asteroid mass would radiate intensely at temperatures reaching trillions of degrees. But where would such objects come from? Not from stellar collapse. Only primordial formation during the Big Bang could create them, and most would have evaporated by now. The connection to thermodynamics runs deep. Hawking radiation proves black holes have entropy, a measure of disorder. This entropy is proportional to the event horizon's surface area. A larger black hole has more entropy than a smaller one. When a black hole evaporates, where does that entropy go? It flows out with the radiation, maintaining the second law of thermodynamics. Think of it like digging a hole in the ground. Normal holes just sit there. But imagine a quantum hole that glows with its own light and slowly evaporates away, getting smaller over time until it vanishes completely. That's a black hole with Hawking radiation. The radiation carries energy away from the black hole. That energy must come from somewhere. It comes from the black hole's mass, converted through Einstein's equation. As the black hole radiates, it loses mass. As it loses mass, its temperature increases. As temperature increases, it radiates faster. The process accelerates continuously. For massive black holes, this evaporation takes unimaginably long. A hole containing 3 times our sun's mass requires 10 to the 67th power years to evaporate completely. The current universe age measures only 14 billion years. Black holes will outlast stars, galaxies, and possibly protons themselves. But primordial black holes with smaller masses evaporate on observable timescales. One weighing about 100 billion kilograms would last exactly until today. Anything lighter has already vanished. Anything heavier continues radiating slowly. Nobody has directly observed Hawking radiation from any real black hole yet. The effect remains predicted by theory, but unconfirmed by observation. This represents one of modern physics' greatest experimental challenges. How do you prove that objects which trap everything actually emit something? The difficulty stems from multiple factors. First, you need black holes with the right mass. Too heavy, and the radiation becomes undetectable. Too light, and they've already evaporated. Second, you need to distinguish Hawking radiation from all other sources. Space contains many things that emit gamma rays and particles. Third, you need detectors sensitive enough to catch incredibly rare events across vast distances. Yet the theoretical foundation seems solid. Hawking radiation follows from combining quantum mechanics and general relativity in curved spacetime. The prediction appears robust. Most physicists believe it occurs even without direct observation. The question isn't whether black holes radiate, but whether we can catch them doing it. And that brings us to the most dramatic moment in a black hole's life, the final instant when all remaining mass converts to radiation in one brilliant flash. From the whisper of radiation to the scream of annihilation, watch what happens when a black hole dies. Watch a black hole through time lapse spanning billions of years. For eons, nothing changes. The hole maintains constant mass, constant size, constant temperature. Then something shifts. The mass begins dropping. The horizon starts shrinking. The temperature climbs higher. This marks the transition from growth to death. The evaporation accelerates continuously. Mass decreases slowly at first. A black hole loses mass proportional to the inverse square of its current mass. Heavy holes shed mass glacially. Light holes evaporate rapidly. The process speeds up as it progresses. Plot mass versus time, and you get a curve plunging towards zero. The descent starts gentle, then becomes steep. In the final years, mass drops noticeably. In the final days, the decline becomes dramatic. In the final seconds, the black hole essentially explodes. During evaporation, the black hole radiates a thermal spectrum of particles. Everything nature allows emerges from the horizon. Photons dominate early when the hole remains cool. As temperature rises, electrons and positrons appear. Higher still, and quarks join the mix. Near the end, even the heaviest particles radiate away. A black hole with mountain mass reaches its final microsecond. It weighs only grams now. Decades of steady evaporation have reduced it from mountain to pebble. The horizon measures smaller than atomic nuclei. Temperature soars into trillions of degrees. Radiation pours out at frantic rates. Each second strips away measurable fractions of remaining mass. The black hole glows across all wavelengths. Gamma rays, X-rays, ultraviolet, visible infrared all emerge simultaneously. Particles of every type spray outward in all directions. The temperature continues climbing. More radiation means faster mass loss, means higher temperature, means even more radiation. Runaway feedback takes over. In the final hour, half the black hole's mass converts to radiation. In the final minute, another quarter vanishes. In the final second, the last substantial fraction explodes outward. The terminal burst releases energy equivalent to multiple nuclear weapons in fractions of a second. All remaining mass converts directly to radiation and particles. The explosion produces a brilliant flash theoretically visible across cosmic distances if instruments could detect it. The gamma ray signature should be unmistakable. Theory predicts a specific spectral shape matching thermal radiation at extreme temperatures. The burst duration should correlate with initial black hole mass. Smaller holes explode faster. Larger holes take slightly longer. Neutrinos accompany the gamma rays. These ghost particles interact weakly with matter, allowing them to escape cleanly. Unlike gamma rays that might scatter on interstellar gas, neutrinos travel straight from explosion to detector. They provide unambiguous evidence of the event. In 2019, a neutrino detector buried in Antarctic ice captured something unusual, an ultra-high energy neutrino unlike anything seen before. This ghost particle carried energy equivalent to several protons moving at nearly light speed. It came from outside our solar system, racing through space at almost maximum velocity. Researchers calculated backward from the neutrino's trajectory and energy. What could produce such a particle? Supernovas seemed too weak. Active galactic nuclei showed wrong spectrum. Gamma ray bursts had inconsistent timing. Every conventional explanation failed to match observations. One team proposed an extraordinary alternative. What if the neutrino came from a primordial black hole exploding in its final moments? As a micro black hole evaporates, it reaches a critical point where remaining mass converts almost entirely to radiation. The terminal burst includes neutrinos at extreme energies. The mathematics aligned perfectly. A primordial black hole with specific initial mass evaporating for billions of years would reach its explosive finale at precisely the right moment to send that neutrino toward Earth. The energy spectrum matched predictions. The rarity matched expectations. This represents potentially the first detection of Hawking radiation, not from a laboratory experiment, not from astronomical observations of stellar black holes, from a microscopic black hole older than stars completing its final act of self-destruction. One ghost particle from an ancient death traveling across space to tell us the story. The interpretation remains controversial. Other physicists suggest alternative sources for the ultra-high energy neutrino. Exotic cosmic ray interactions might produce similar signals. Unknown astrophysical processes could generate the required energies. The primordial black hole explanation fits, but cannot be proven definitively from one event. The ice cube detector uses 1 cubic kilometer of Antarctic ice as target material. When a neutrino finally interacts, it produces a flash of light detected by surrounding sensors. The light pattern reveals the neutrino's direction and energy. The 2019 event deposited enough energy to be clearly visible, despite neutrinos' weak interactions. Analysis showed the particle came from deep space, not Earth's atmosphere. Calculating backward from its trajectory and energy, researchers proposed it might have originated from a primordial black hole, exploding within a few hundred light years of Earth. The timing, energy, and rarity all matched predictions for terminal burst neutrinos. Finding more such neutrinos would strengthen the case dramatically. If several appeared with characteristics matching evaporation, model's coincidence becomes unlikely. The statistical significance would grow with each detection. Eventually, the evidence would become undeniable. Neutrino telescopes around the world now search specifically for these signatures, and perhaps we've glimpsed something profound. The first direct evidence that black holes truly evaporate, that nothing lasts forever, not even objects that trap light itself, that the universe operates according to laws even stranger than we imagined. One ghost particle from one ancient death, telling us that even darkness eventually returns to light. Where particle meets void, where quantum meets gravity, the universe reveals its deepest puzzles. Stand at a black hole's event horizon, and quantum mechanics goes haywire. Virtual particles that normally wink in and out of existence separate permanently. Vacuum energy density fluctuates wildly. Space-time itself exhibits quantum uncertainty. Physics enters truly unexplored territory. The horizon represents a boundary in space where gravity becomes so strong that not even light escapes. Mathematically, it's a smooth surface with no special properties locally. An observer falling through would notice nothing unusual at the crossing point. Yet viewed from outside, the horizon displays extraordinary quantum behavior. Here at this boundary, the two pillars of modern physics meet. General relativity describes gravity through curved space-time. Quantum mechanics describes matter through probability waves and uncertainty. Both theories work brilliantly in their domains, but at the event horizon both struggle. Neither alone provides a complete description. Quantum field theory predicts that empty space constantly produces particle-antiparticle pairs. These virtual pairs borrow energy. From vacuum uncertainty, exist briefly, then annihilate. The process happens everywhere continuously. Near black hole horizons, it leads to Hawking radiation. When a virtual pair forms very close to the horizon, they might separate before annihilating. One particle falls inward, the other escapes outward. This process creates profound puzzles. Energy seems to come from nowhere. Information seems to vanish. Quantum entanglement seems to break. Each violation challenges fundamental principles. The information paradox strikes at quantum mechanics' heart. Quantum theory says information cannot be destroyed. Everything that happens leaves traces in the universe's quantum state. But black holes seem to violate this rule. Matter falls in carrying information. That information disappears behind the horizon. The black hole eventually evaporates, leaving only thermal radiation. The radiation carries no memory of what fell in. A hole formed from matter radiates the same as one formed from antimatter. An old hole from stellar collapse looks identical to a primordial hole formed from pure energy. The radiation carries no information about initial conditions. Where did the information go? Several proposed solutions compete. Maybe information leaks out, gradually encoded in subtle correlations between emitted particles. Maybe it emerges in a final burst when the whole reaches Planck scale. Maybe it transfers to another universe or dimension. Maybe the entire picture needs revision. The firewall paradox adds another layer of confusion. Some physicists propose the horizon might not be smooth and empty. Instead, it could be a wall of high-energy particles. This firewall would incinerate anything falling through. But this contradicts general relativity's prediction of a smooth horizon that falling observers cross without incident. Physicists argue intensely about whether firewalls exist. Some say they must to preserve quantum mechanics. Others say they cannot because general relativity forbids them. But here's something reassuring. Nobody can go there to check. The nearest black hole sits thousands of light years away. Even if you could reach it, you couldn't send back information after crossing the horizon. Entanglement across the horizon creates additional problems. Particles inside and outside the horizon can remain quantum mechanically entangled. Measuring one particle instantly affects the other, despite being separated by the horizon. This non-local connection raises questions about causality and information flow. The holographic principle offers one resolution. It suggests that all information in a region of space can be encoded on its boundary. The black hole horizon acts as such a boundary, potentially containing all information about the interior. If holography is correct, then studying horizon quantum effects reveals fundamental truths about space and information. The horizon isn't just a physical boundary, but an informational one. Everything that falls in leaves an imprint on the horizon's quantum state. The information doesn't vanish, but gets encoded in the horizon's structure in ways we're still learning to understand. Different approaches to quantum gravity make different predictions. String theory replaces point particles with tiny vibrating strings. Applied to black holes, it predicts the horizon has microstructure. What appears smooth classically consists of many quantum degrees of freedom at microscopic scales. Loop quantum gravity provides an alternative. It quantizes space-time itself, replacing continuous geometry with discrete quantum chunks. Black hole horizons in this framework consist of quantum geometric states. The horizon becomes a quantum mechanical object with specific discrete properties. Both approaches predict modifications to Hawking radiation at extreme scales. The corrections remain tiny for stellar mass black holes. For Planck scale black holes, the corrections dominate. Observing terminal explosions from evaporating primordial black holes might test which quantum gravity approach is correct. These aren't just abstract mathematical puzzles. They're questions about reality's fundamental nature. What happens when the universe's two most successful theories both apply to the same situation? Which one wins? Or do they somehow merge into something new? The answers wait at boundaries we cannot reach, encoded in radiation we've barely glimpsed, hidden in quantum effects, too subtle to measure directly. Yet we keep searching, calculating, observing, hoping to catch nature, revealing its deepest secrets at the place where everything we know breaks down and something new begins. From quantum mysteries at horizons to the biggest mystery of all, the invisible substance holding galaxies together. Galaxies spin too fast. Stars orbit galactic centers at speeds that should fling them into intergalactic space. Yet galaxies hold together. Something invisible provides extra gravitational pull. We call it dark matter. 5 times more dark matter exists than normal matter. It surrounds galaxies in enormous halos. It permeates galaxy clusters. It shaped cosmic structure formation. Yet nobody knows what it's made of. 85% of the universe's matter is invisible. It's like reading a book where 85% of the words are written in invisible ink. You see some letters, some words enough to know there's a story. But most of the text remains hidden. You know it's there because the visible words reference it. The grammar requires it. The plot depends on it. But you cannot read it directly. Decades of searching have not identified the particle or particles responsible. Physicists built detectors deep underground to catch dark matter collisions. They found nothing convincing. They designed satellites to look for dark matter annihilation in space. They saw hints, not proof. Every experiment constrains possibilities, but doesn't solve the mystery. Primordial black holes offer one solution. They gravitationally affect their surroundings, identically to dark matter. They interact only through gravity. They formed early enough to seed galaxy formation. They exist across a range of masses that could explain observations. The idea seems almost too simple. Why invent exotic particles when ordinary black holes could work? But several observations constrain how much dark matter can be black holes. Gravitational microlensing searches surveyed millions of stars for brief, brightening events caused by compact objects passing through the line of sight. The detection rate limits black hole abundance. Current data excludes primordial black holes as dominant dark matter in certain mass ranges. However, lighter and heavier ranges remain allowed. Black holes with masses between Earth's mass and 1/10 our Sun's mass evade most constraints. They're too heavy to have evaporated too light to produce frequent microlensing and formed at just the right time to seed cosmic structure. Between the upper limit from microlensing and the lower limit from evaporation lies a window where primordial black holes could hide. This window might contain enough to explain some dark matter observations while remaining below detection thresholds. Another cosmic mystery involves ultra-high energy cosmic rays. A proton slams into Earth's upper atmosphere. Its speed approaches light velocity so closely that time itself dilates. This single proton carries energy equivalent to a baseball thrown at 60 miles per hour. Condensing that much energy into one subatomic particle requires processes operating at extremes. Most cosmic rays carry moderate energies. Some reach extraordinary levels. The most energetic ones challenge everything we know about particle acceleration. Their origin remains one of astrophysics' deepest mysteries. In 2021, a cosmic ray detected in Utah carried energy exceeding 240 exaelectron volts. This surpasses previous records significantly. No known astrophysical object produces such energies easily. Standard acceleration mechanisms struggle to explain ultra-high energy cosmic rays. Supernovas can accelerate particles to high energies, but not ultra-high. Active galactic nuclei seem promising but too distant. Gamma-ray bursts might work but occur too rarely. Primordial black holes offer one intriguing explanation. As these black holes evaporate, they emit particles across enormous energy ranges. The final death throes produce particles at ultra-high energies, matching the mysterious cosmic ray observations. A black hole exploding relatively nearby could generate such events. Cosmic rays are like bullets fired through the universe, but nobody knows who pulled the trigger. They arrive from all directions. They carry no information about their sources because magnetic fields deflect charged particles as they travel. By the time they reach Earth, their trajectories have been scrambled. Galactic and intergalactic magnetic fields complicate interpretation. Charged particles deflect in these fields. Ultra-high energy particles deflect less than low energy ones. but still deflect measurably. Tracing cosmic rays back to their sources requires modeling these magnetic effects. The connection between dark matter, cosmic rays, and evaporating black holes might solve multiple mysteries at once. If primordial black holes comprise some fraction of dark matter, their terminal bursts would produce ultra-high energy cosmic rays and neutrinos. The 2019 ultra-high energy neutrino detected by IceCube might represent this connection. Multi-messenger astronomy allows cross-checking different detection channels. A coincident detection across gravitational waves, electromagnetic signals, neutrinos, and cosmic rays would provide definitive tests. Catching one event simultaneously in multiple channels would prove origins conclusively. The telescope array in Utah and the Pierre Auger Observatory in Argentina monitor ultra-high energy cosmic rays continuously. Both detect roughly 1 particle per square kilometer per century at the highest energies. This rate constrains source populations and emission mechanisms. Ultra-high energy cosmic rays do not correlate strongly with obvious sources. They don't point back toward the galactic center or toward known active galaxies. Their directions appear nearly random despite their extreme energies. This randomness actually supports the primordial black hole hypothesis. If black holes scatter throughout galactic dark matter halos, their explosions would occur everywhere. No preferred direction would emerge. Future experiments will improve sensitivity and angular resolution. Better tracking cosmic rays to their sources will test the primordial black hole hypothesis directly. If trajectories cluster toward regions where black holes might hide, evidence strengthens. Random arrivals from nowhere support the hypothesis that they come from everywhere. The invisible majority of the universe might be made of the oldest compact objects from the universe's first instant floating through space, occasionally exploding and sending particles our way. Each cosmic ray might be a messenger from an ancient death. Each neutrino might tell the story of a black hole completing its journey from creation to annihilation. And through all these mysteries, one question persists. What is the rarest thing? Now, at the journey's end, we ask the deepest question. Among all these impossible things, what truly deserves the title rarest? We've journeyed through quite a landscape tonight, from laboratories beneath Switzerland trapping antimatter, worth more than nations, to elements that destroy themselves before you can see them, to matter that could convert planets in fractions of a second, to stars compressed beyond imagination, to black holes that evaporate into light. Now we must answer the question we started with. What is the rarest thing in the universe? Antimatter costs $62 trillion per gram. Only 9 complete anti-helium atoms have ever been created. That's rare, but nature produces antimatter continuously in lightning storms and cosmic ray collisions. It exists just in tiny amounts. Astatine appears in quantities of 1 tablespoon across the entire Earth. That's incredibly rare, but uranium decay constantly creates more. It's always present somewhere, even if fleeting. Strange matter might not exist at all, or it might fill entire stars. We don't know. That's a different kind of rarity, the rarity of uncertainty. Promethium refuses to exist naturally for long, cursed by physics to brief appearances, rare not in space but in time, forbidden from persistence. Primordial black holes might comprise dark matter, or might not exist at all. Their rarity depends on conditions in the first second. After the Big Bang conditions, we can only guess. Now, imagine combining all these: a strange star containing primordial black holes surrounded by antimatter emissions, producing astatine through nuclear reactions, all happening simultaneously. Calculate that probability. Multiply the individual rarities together. The result becomes infinitesimal. In our galaxy, containing 200 billion stars, perhaps such a combination doesn't exist. But expand the search to the observable universe. 2 trillion galaxies extend across 90 billion light years. The total number of stars exceeds comprehension. Surely, one bizarre combination must exist somewhere. Statistics suggest extraordinary coincidences occur given sufficient opportunities. But we can only observe our local cosmic neighborhood in detail. Within a few thousand light years, every star can theoretically be examined. This volume limits what rare combinations might appear. Yet even in this limited sample, astonishing objects have been found. Perhaps the rarest natural object must involve a chain of improbable events. Each step requires specific conditions met accidentally. The probability of the complete sequence becomes negligibly small. Yet somewhere in the universe's vast expanse, even negligible probabilities manifest as reality. But here's a thought that should make you pause. Perhaps the rarest thing isn't a substance or object at all. Perhaps it's something else entirely. Something we've been demonstrating throughout this entire journey: consciousness, awareness, the ability to ask, what is rarest? Think about what had to happen for you to exist right now listening to these words. The universe had to permit stable matter. That tiny imbalance in the first second, one extra matter, particle per billion, had to occur. Without it, only light would exist. Stars had to form fuse elements, explode, scatter those elements into space. Your body contains atoms forged in stellar furnaces billions of years ago. Carbon, oxygen, nitrogen, phosphorus, all made in stars. A planet had to form in the habitable zone of a stable star. Life had to emerge from chemistry. Single cells had to evolve into complex organisms. Mass extinctions had to spare your ancestors. Millions of years of evolution had to produce creatures capable of questioning reality. And you specifically, you had to be born. The probability of your exact existence with your specific genetic combination, your experiences, your thoughts approaches zero. Yet here you are. 85% of the universe is invisible, like 85% of a book written in invisible ink. But you're part of the 15% that can read itself, matter that became aware, atoms arranged to contemplate atoms, the universe observing itself through your eyes. The anthropic principle suggests we observe this particular universe because it's the only type that permits observers. If physical constants were slightly different, stars might not form, heavy elements might not exist, life might be impossible. The fact that we can ask, why are we here, means we're in a universe compatible with our existence. After all this exploration, maybe we're the rare and strange things, carbon-based creatures who dare to ask what's rarest, who build particle accelerators to recreate Big Bang conditions, who send telescopes into space to catch light from the universe's first moments, who wonder about antimatter and black holes and the nature of existence itself. The story has taken you from Swiss laboratories to quantum horizons, from substances worth more than all Earth's economies to things that cannot be bought at any price, from the densest matter possible to the emptiest vacuum, from the beginning of time to its end. Like searching for treasure, your whole life digging everywhere, exploring every possibility, then realizing the real treasure was the journey itself and the wonder you felt along the way. The rarest thing might simply be the ability to wonder at all. We are cosmically improbable. The specific arrangement of atoms processing these words could easily have never existed. Yet here, we are contemplating the universe's strangest corners. That improbability makes every moment precious, every thought unique, every observation irreplaceable. And now, with all these wonders of the universe before you, from antimatter that annihilates on contact to black holes that evaporate into light, from neutron stars that weigh billions of tons per teaspoon, to quantum horizons where physics breaks down, let them all settle gently in your mind, like distant stars in a peaceful sky. Each phenomenon, however rare, is part of this magnificent universe, and you, with your miraculous consciousness, are the one witnessing it all. Rest now with gratitude for the beauty and mystery you're part of. Let these thoughts drift softly away, like promethium atoms decaying into dreams. The rarest things in the universe exist at reality's edges, but perhaps the rarest thing of all is you right now capable of appreciating them. Sleep well, knowing you've touched the boundaries of the possible and returned with wonder intact. The universe continues its dance of creation and destruction, rarity and abundance, mystery and revelation. And somewhere in that vast cosmic story, you matter. You're part of it all. Good night.